Hi, I'm Brian Mullin, and this is Balls Out Physics, Episode 5, Propulsion in Space. Now, a lot of people out there, including myself, when they started questioning things, questioning space travel, start to think about how in space there's nothing, or there's no matter in space. And a lot of people have said, well, what are you pushing off of in space? And that's one of the things I started to think about a lot, and it's one of the things that kind of broke my heart, because if you watched episode 4 when I talked about the thermosphere, I realized that the temperatures in low Earth orbit were too high, but I did wonder if we can get through the thermosphere, can we still travel the stars? But then I started to think about this idea of having nothing to push off of, and I realized that I don't think it's even possible to move in space if it is what mainstream science or mainstream astronomy believe, that it is a vacuum. It shouldn't. You start to think that it shouldn't be possible to move, and I thought of Newton's third law, which basically says that every action has an equal and opposite reaction, and that's definitely true on Earth. If you push on something, it pushes back with the same force, or pushes back. It creates an equal and opposite reaction. If there's eventually it will. If you push on something that's not strong enough to resist your force, then you'll move, or it will move, until enough force is developed until enough reaction is developed to resist your force. So, for example, if I crouch and then push up on the bottom of my feet to push myself back up, that the reaction of the floor pushing back up is equal to the force of my feet pushing down. That's basically what Newton's third law says. Okay, so a lot of people say, well, in space, how can you move when you've got nothing to push off of? And what we're told, what the accepted theory is that if all you have to do is push mass away from you, and you'll move in space. And it kind of makes sense, but then Newton's third law comes back, and so there's a lot of circular reasoning for me trying to figure this out. Like, what am I missing? Because I didn't want to accept that you can't move in space, but I honestly don't think you can. But start with a jet engine on Earth. Now, on Earth, we have air all around us. It's a fluid, really, and it's not that much different from water. When you really start to think about it, gas and liquid are very, very similar. They're both fluids. And so, say this is a jet engine, a very crude drawing of a jet engine on a commercial airliner. And when I'm standing here, when you're standing at sea level, the pressure on your body from the atmosphere, the weight of the atmosphere above you, is roughly around 14.7 pounds per square inch, or 101 kilopascals if you're using the metric system. And so really what's creating that pressure is the weight of the air above you, all of the air above you. It's just like, the best way to think about it is that if you dive in a pool and you swim to the bottom, you can feel the pressure increase as you go lower and lower in the pool. That's because the weight of the water above you is increasing, and you really feel it in your ears. Especially if your ears are very sensitive, you go lower and lower, you go deeper and deeper, you go, depending on how deep the pool is, you feel that pressure in your ears. It's the same thing in the air, just not as noticeable. And so, as you rise in a pool, the pressure becomes less. And the same thing happens in our air. If you go up into the mountains, the pressure actually decreases, and when engineers are designing things that are affected by pressure, they do account for altitude and how pressure changes. And at sea level, we use 14.7, and that's typically called 1 atmosphere of pressure. Okay, so a jet engine sitting here, say the engine sitting on the runway, is experiencing this pressure all around it, just like our bodies are. And that's one of the reasons it's theorized that you need a spacesuit in space. One of the reasons is because our bodies in space would expand because space has negative pressure. And so, the atmospheric pressure is what actually holds our bodies together on Earth. That's the theory. So you have all this, call this the air pressure, this atmospheric pressure, if we want to call it that, or whatever, is acting on this engine from all sides. Okay, as it's sitting here on the runway. Just like it's acting on my body, it's acting on you, the viewer, and everything. Okay? So there's pressure here. And that is 1 ATM equals 14.7 psi. I'm going to use English units because that's what I'm used to. But I do think the metric system is better because, well, I think if you do believe that this world was designed, I think the designer gave us a hint on which system is better. It's just easier for our heads, but each their own. So, okay, have an engine sitting here. It's off. Alright, I posted a link below to a 5-minute video that shows how a jet engine works in a nutshell, and it's very cool how they work. It's very interesting. It's really based on how a nozzle works. So to give you a good example of that, you take a garden hose and you turn the hose on full, and water streams out of the end of the hose. But if you put your thumb over the end of the hose and cover, say, half of it, the water sprays out much faster. And the reason that happens, it sprays out faster and farther, is because you increase the energy, but the amount of mass flowing through stays the same. You think about it, behind your finger, there's still the same amount of mass, the same amount of water is flowing. But then you reduce the size of the hole that the water can come out of, but that same amount of mass still has to keep moving because there's still that much mass behind it, pushing it. So that's why the water sprays farther and faster, because you're actually increasing the energy. And if you think about it, kinetic energy is equal to KE is equal to 1/2 mass times velocity squared. So you see what happens here is the velocity increases because you reduce the area, and so your energy increases. Now I could get into the flow equation and show how when you actually reduce the area it increases the energy, but I'm just giving the basics here. This is what's happening, and that's how a jet engine works too. In a nutshell, there's a little more complicated than that, but what happens is the intake in the front of the engine, where the fan is. If you see you see the front of a jet airliner, it has a fan here, and so fan turns on, and these things really suck an enormous amount of air into them. Okay, they suck in this air, as you see in the shape of the engine. If you watch that video, about 80% of the air just flows around the turbine in the center. And so, just to keep it simple, we just say that the air comes in a big opening and then comes out of a smaller opening, so it's forced out the back at a higher velocity. The energy is increased. Okay? Keep it simple. So we'll just use here for this. So this air is forced. This air is forced out the back. Now this little turbine, this cone represents the turbine, and there is some difference. About 80% of the thrust comes from the air flowing through, and then about 15 to 20% of the thrust comes out of the turbine. But for this, we'll just say it all. If the thrust is being forced out of the back of the engine, okay. And so per Newton's third law, every action has an equal and opposite reaction. So this thrust creates a reaction on the engine. I'll just put it right here. Call this the reaction R, and pushes the jet, and eventually pushes the jet forward. That's not the only action happening here. The typical example, or the classical example, is that the thrust pushes this way. The action of the thrust pushes this way, creates a reaction to push the rocket. Okay, but there's something else happening here. There's a lot of actions happening. The thrust is acting on the environment, or the air is acting on the thrust, however you want to look at it. So the way I see it is it's like this column of air, this jet of air is being sprayed out of the back of the engine, and you have this atmospheric pressure that's pushing the surrounding relatively stationary air against it, or holding it against it. So you develop little reactions, friction between the air. This is kind of like the viscosity of liquid. Actually, it's pretty much what it is. So little shears, as I call it. And that's how you develop the reaction between the thrust and the air. Does that make sense? So like the pressure holds the stationary air, relatively stationary air, against the thrust, and that creates friction, which creates a reaction against the thrust, which basically you have to keep your action reaction going to move. Make sense? So that's how it works in a nutshell on Earth. There's a lot more to it, but watch that video to understand how the jet engine works. Okay? But in space, it's different. Space sucks. Literally, it sucks. It's a vacuum. The pressure is negative. So all these blue arrows pointing at the engine would be different. So just they'd be facing the other way, because space would be sucking on the engine. Now a jet engine like this can't work in space because you need an intake. You need to pull air in and force it out the back. So that's not how propulsion in space works. And when I was a kid, I grew up watching the space shuttle launches, and I was quite obsessed with it. I wanted to be an astronaut like every kid for a little while. And I liked watching how it moved. I liked learning how it worked in space. And if you remember the space shuttle program, the way the space shuttle worked after the launch, after it got into space, it had these little jets. It had these little jets all over it that shot compressed oxygen out into space, and that was supposed to be the mass moving, the push of the mass away from the mass of the oxygen away from the shuttle was supposed to be what controlled its movement and gave it thrust when it needed to, rolled whatever it needed to do. The little tss, you see in the movies. Well, so let's say that this is actually one of the little nozzles on the shuttle, okay? And then we'll extend the nozzle over to the shuttle. Say the shuttle's over here somewhere. This is just one of those little nozzles, tiny little nozzle that shoots compressed oxygen out into space, okay? And remember though, space sucks. So you have this pressure acting the other way. What that pressure is really not important because it sucks. That's all that matters. I'm being... So we have all this suction happening on the engine, and on the engine and on the, or not on the engine, on the nozzle, excuse me, and it's pulling on here and say the nozzle's closed right now. This nozzle isn't active yet, and so you have this built-up compressed oxygen inside this nozzle, and say there's a tank over here filled with compressed oxygen, and when they open the end of the nozzle, or the jet, whatever you want to call it, you have this suction force over here, and then I'll use red to show that the very high pressure oxygen wants to spray out into space. But space is already pulling away from that oxygen. So how do you develop an equal and opposite reaction when space is already pulling all of this stuff away? It's sucking, it's pulling. So this opens, and there's compressed, built-up oxygen in here, and oxygen is actually pushing on the wall of the nozzle and the tank that it's in. Okay? It's already pushing on that surface. And then it opens and it sprays out into space, but there's no air out there. There's no positive pressure to hold air against the oxygen if there was any air. And so it would just, in my opinion, when you really start to think of it, wouldn't it just expand infinitely the moment it starts to come out? Where's the opposite reaction created? And that's what people are really asking. Our guts, that's like a lot of people, our gut reaction is, no, wait, that doesn't seem like it would work. And so this question is discussed. I actually have a friend who took a propulsion class. I can't remember what the class was called. He took it was an online class. It was free from a very well respected university. I won't mention it. Well, it was MIT, but they offer free courses. And he told me that in the course that to answer this question, what they do is the professor has a video of himself standing on a skateboard, and he took some weights and throws the weights away from him, and he moved back the other way. And I said, oh, I got to try this. And so I took I had an old skateboard, and I went out into the garage and I started throwing weights away from me, and I didn't move. And I was like, They can't lie about something like that. That would be, people would test that eventually, right? Come on. And so I may have said this in the past that I didn't move on the skateboard. So the skateboard had really old wheels on it, and these are the wheels that used to be on it. You can see the bearings are kind of rusty, and so I decided I really need to do this right. So I got some nice rollerblade wheels. When I was a kid, it was considered lame to put rollerblade wheels on your skateboard, but I kind of sucked at skating, so I just liked going fast. And this skateboard is the design here. My idea here is for this thing to only go straight. Because you see, if I try to turn, the board will hit the rollerblade. But so I got some new bearings. You know, wheels spin really well, and I set up a trap or something to catch stuff as I threw it away from me. And I stood on the skateboard and started throwing mass away from me. Well, I took a cinder block or a CMU block and threw it away from me, and sure enough, I moved backwards pretty significantly. So I was like, okay, that works. But is that the same thing? Well, it took me a while to wrap my head around. I'm like, where's the equal and opposite reaction? And is this the same thing? And I don't think it is. And here's why. Best way to think about it, let's start with a bullet. Okay, here's a bullet, all right? With a bullet, you have a brass casing, and you have, this is actually considered the bullet, and this is the casing, or the cartridge, right? The brass casing. And this right here is the joint between the two of them, okay? And on the back, you have a primer, this little circle here, and the firing pin strikes the primer and ignites the gunpowder within within the cartridge, and the gunpowder explodes, and it pushes in all directions. But since this bullet, since there's a seal here, and this is the weakest point between these two masses, the bullet flies one way and the casing tries to fly back the other way. If you've ever shot a gun before, if you're holding a rifle against your shoulder, you know, you get a kickback, but the smaller mass of the bullet's mass is much smaller than you, the rifle, and the casing, so the bullet flies away from you. And so one of the, you know, when people ask this question, when I asked this question, one of the things I got was, well, if you put a bullet in a vacuum chamber or in space, and or a gun, and you were able to strike the primer, and there was, you know, oxygen contained, and say the bullet was completely sealed, the bullet and the gun would fly away from each other. I said, yeah, it would, because you have two masses with an action happening between them, so you get two reactions there. Does that make sense? And so I started thinking about that, and I said, well, a skateboard's the same thing, really, as the bullet. The action is my arms, or the professor's arms, pushing on that mass, and the reaction is occurring between the action of your arms on you and on me and the CMU block or the tire that I threw, or whatever, or the weights, whatever you throw. You actually create two reactions there. Okay, there's an action between them, but here it's not the same. Before, in my opinion, it's not the same. Before the shuttle leaves the Earth, they fill the oxygen containers with oxygen, and the nozzles and everything with oxygen, and it becomes pressurized. You know, the oxygen is forced into the container, and the oxygen expands. High pressure pushes on the outside of the container, and then the container pushes back against these little pressures that I show here. The container pushes back, so the action and reaction has already occurred. Okay? And it's just waiting there, and this is now potential energy waiting to be released. So the action and reaction has already occurred. This isn't the same thing as somebody standing on a skateboard and throwing something away from him, or a bullet. It's not the same, in my opinion. When you really think about it, you see what I'm saying here. You need two masses with an action happening between them to move in space. On Earth, this nozzle would spray against the air, and you would get an equal and opposite reaction, because there's positive pressure on Earth and there's air. In space, there's not. It's completely the opposite. It's just like, it's very similar to the jet engine on Earth, except you don't have the intake, you just have compressed oxygen spraying out against the air. In space, it's not the same. And I don't think it works. It's kind of hard to wrap your head around this one, but what's amazing is so many people have this gut reaction, like, yeah, that shouldn't work. And I had a hard time trying to wrap my head around why my gut was telling me it didn't work. And it's pretty amazing that we have that ability to know something's not right. We can feel it, but we can't actually get our minds to see right away what the problem is. I find that very interesting because statistically, with multiple choice exams, when someone comes to a question that they don't know the answer to right away, your gut reaction, your first instinct, if you have four choices, a multiple choice test, A, B, C, or D, your gut reaction, the first one you see that looks good, usually is the right answer. It's pretty amazing. It's sometimes called intuition, and women are known for having better intuition than men. So, ladies out there, how does this feel? What do you think about this? Does this make sense? Does it seem like we should be able to move in space with this type of propulsion? Now, if you had a bunch of bullets and and barrels sticking out of the space shuttle and fired bullets out of those barrels, then I would think you would be able to move for the reason I explained. But carrying bullets and gunpowder up into space, first of all, it's really heavy. Bullets are heavy. Lead, for one, brass casings, gunpowder, everything. And all the high temperatures you're seeing up there and the high pressures and everything and these extremely flammable bullets, have fun with that. I wouldn't do that, and I'm sure nobody would want to do that. So you would need two masses and an action happening between them to move in space, whereas in this case you only have one mass that's already contained, it's already pressurized, the action and reaction has already happened, and then when you open the nozzle, it just sprays out into space. Make sense? So that's the problem I see, and today is April 1st, so I kind of figured out how to explain this. Droidfuel and I were actually talking about this one, and then it kind of worked out that what we both see. A lot of people feel that something's wrong about propulsion in space, or the classical ways we've been taught with compressed oxygen being sprayed out into space, and that's how the shuttle moved. I know there's different propulsion systems out there, but space shuttle was supposed to exist and it was supposed to move up there, and a lot of people are thinking that it wasn't real. And based on everything I've shown in episode 4 and what I've seen, all the hoax footage, I don't think it's real, unfortunately. And so had to cut. So yeah, as I was saying, today's April 1st, and I think we're all being fooled by these space agencies, and there are a lot of people who agree with me. I mean, it's the number seems to be growing more and more every day. There's in the description below, I posted another link to a video showing glitches and anomalies and things that don't look real on the space station, that was made by a person who actually who does think that we live on a globe. I remain open. I have no idea what this world is at the moment, and I'm trying to determine that, so keep reiterating that. And so yeah, I think we're being fooled. Another thing I want to point out is if you watched episode 4, there's two episodes up right now. There's probably more sub-episodes for episode 4. I talked a lot about the International Space Station and the temperatures and all the problems with low Earth orbit. But the International Space Station is supposed to have an ion thruster on it, and it seems very high tech. I've looked into it a little bit, but I don't really want to spend too much time trying to understand how it works, because if the compressed oxygen propulsion has problems, I mean, and what's the point really is how I feel about it now. But the reason that the ISS has an ion thruster is NASA says is because the space station runs into gas particles in the thermosphere. There's collisions with gas particles that are significant enough to slow it down. And if you watched episode 3, in episode 3, I talk about how the minimum velocity, or the velocity at whatever altitude is calculated to, or a minimum velocity that you need to maintain to stay in orbit, so you don't get pulled towards the Earth or whatever object you're orbiting. And so the space station has to maintain that minimum velocity, or it will get pulled towards Earth. If it increases the velocity, then based on the heliocentric model and our gravity equations, then it would move farther away from Earth. So they have to activate the thruster every 3-6 months. I don't remember what it is, due to collisions with these gas particles. So if you watched episode 4, the whole episode was all about, how come this station doesn't get hot? How come satellites don't get hot? And so these collisions with particles are significant enough to slow the station down, but not significant enough to heat it up, because the particles contain a lot of energy. It's very hot up there. So there's a lot of contradictions, a lot of things that don't make sense. And then when you see video, when you see things that show glitches and makes it look, just anomalies that look fake, pay close attention. That video, the first time I watched the video I posted down below, I didn't really see a whole lot, and then I really started paying attention to what the video creator was actually trying to show. I said, wow, yeah, there's things that it does look fake, like it's been faked, or it's pieced together, or like they're in a pool. So I'll let you be the judge of that. I'm not telling you what to believe. Like I said, this is my opinion, but there are people out there who agree with me. It's a lot of people are agreeing with me, and I'm agreeing with others who are doing work like this. So we need some answers, and like, we're paying for all this stuff, and when still only 553 people have been to space. So we need to stop paying to be fooled, I think, if we are being fooled. And at the moment, I have to conclude that. So regardless of the shape of the world, I'm going in kind of a different direction as well. I'm going to keep making Balls Out Physics episodes, but I'm also besides what the shape of this world is, I'm kind of leaning towards trying to understand how it works. And if these space agencies are going through all this trouble to fool us, maybe it's because they do know how this world works. Could be. Or could not be. There could be logical explanations for all of this stuff, but that's why I'm making these videos, to see if we can find them or see if we can't. So, until next time, peace.